One of my clients recently mentioned to me that one of the biggest challenges with dealing with things like Confluence or any other large data source is they don't even know where to start. They don't know which page has what content. The Confluence space has thousands of pages and they don't know the content of each page. They're not sure what to search for. They have a lot of trouble dealing with these sort of large data source environments like Confluence or any other source that you can think of, which is similarly natured. Now, I've built an agent with DSPy and RLMs that help you traverse this sort of long data source or long context problem in a very, very powerful, very, very scalable way. So, with that in mind, let's get started exploring Confluence spaces using DSPy RLM or recursive language models. As always, I always have a demo to show you, but before I do a demo, I just want to explain this because it's a concept that is not very common. It's not something that I explore a lot. At the same time, it's something new to me as well, so it helps me kind of frame my thoughts when I have the slide deck with me. So, the challenge that we're trying to solve today, or the project that we're taking up today, is going to be basically traversing a bunch of Confluence spaces. So, Confluence, for those of you who don't know, is a large wiki tool that companies use or large enterprises use, right? Large enterprises typically have Confluence environments with multiple spaces, and each space has thousands of pages. And this has anything from sales documentation to code documentation to PRDs to planning docs and all of that stuff. So, Confluence is used by very large companies to handle wikis or handle knowledge bases that are of massive sizes, right? So Confluence, that's what it does. Now we are going to look at the challenge here, right? So one of the big challenges with dealing with something like a Confluence or any other large data source like that is that you have a ton of data to deal with, right? So you have hundreds of thousands of pages, nested spaces, nested pages, cross references, you have all of that stuff. The context is a huge problem, and with llms, as always, long context becomes a huge problem. Now I know a lot of llms tend to have 1 million 2 million context windows, but that doesn't mean that just because they have long context windows they're going to do a great job of retrieval or analyzing a specific issue, simply because the long context problem essentially works like a U curve, right? When data is at the beginning or at the end, it typically is able to identify it pretty easily. But if there's something in the middle, then it may not be able to do a very good job of retrieving that data or doing inference with that data set very well. So it ends up being a big problem, and there is context rot, which basically means that there's very little signal and there's a lot of noise with large context challenges. So this is why you have DSPy, which is an algorithm that can help you. I mean, not DSPy itself, DSPy is RLM, which is recursive language models, that can help you do this in a much more significantly better way. So these are some of the issues. Like I said, context rot, no adaptive retrieval, cost. Tokens, again, remember, tokens are expensive, especially when you're using expensive models like, let's say, GPT 5.2 Pro or whatever it is, or Opus or something like that. You're going to get a huge bill if you use long context with that, especially with massive data sets. So it becomes a big challenge. So the idea of RLM or recursive language models is that they treat the context as programmable. So imagine that you have all of these Confluence documents loaded as a massive string in Python. What the LLM would do is basically work through it like a data analyst or a data scientist, right? Basically, it would first say that, okay, I'm going to use these keywords to look for sections of the document or sections of the string that has this. And then it would write another Python program that would drill down further based on what it identifies. Then another Python program to drill down further based on what it does. So it operates on a single variable, and the intermediate or the reasoning steps are basically it writing Python code and executing Python code in order to search for things and get to a better answer. In fact, this approach is what a lot of folks are using even in erstwhile traditional RAG systems, where they're giving an agent access to a file system and having it use typical tools like grep and so on to be able to search for things and find the answers within those environments. This is very similar, except that it does it in the context of a single variable, and that variable it uses code and code execution to drive down and actually come up with the actual answer. So it uses a Python REPL and then uses the variables, so there's no challenge of massive tokens being used, because it writes code and executes code, analyzes the response, and then writes more code. And all of these are typically shorter programs, so you will not see massive context being used or massive tokens being used. So it's a lot more efficient from a token perspective. At the same time, it's also a lot more accurate in my view, simply because it's able to drill down to the actual issue very quickly, or the point of the question very quickly. Especially if you use language models that have good reasoning capabilities, it's able to do this really, really well, right? So that's something that you'll see. So the idea is that it stores context as a variable. LLM uses code, so it basically behaves like a human data analyst of sorts, explores that single variable through multiple regex searches or through different types of searches. Then it executes that code, it gets the responses, then executes more code, gets more responses, and then finally, once it has a good enough answer, it says, hey, this is what I have and this is the answer I've come up with. And then of course it adds the LLM's capability to refine the data and actually give you an answer. So this is how RLM does it. The idea of RLM and why I like it a lot more than I like RAG, and if you've seen my previous videos, you'll see that it's a theme with me, is that RAG, again, one of the big challenges is you need to pre-build the index, you need to have embedding, you need to make sure that those embedded data sets are properly refreshed, you need to decide a chunking strategy. It's a lot of stuff that can go wrong. So this is really where RLMs can shine, and I'm going to show you an example where RLMs do shine. So let's get to our example where I'm going to explore a Confluence space, and I'm going to show you how I use RLMs to do it. All right, let's get to the demo. And before I start off with the demo, I just want to show you the Confluence environment. So this is my Confluence space. This is not an active space. I'm not showing you some sensitive data here. It's basically a test space that we use to actually test our security design review product called security-review.ai. So this has a bunch of synthetically generated documents. So you'll see that this is a space that has a whole bunch of PRDs. It has some documentation, so on and so forth. It has, each space has its own documents, its own wikis. In some cases, it happens to be a knowledge base. In some cases, it happens to be documentation and so on. So that's what this Confluence space is. Now, the idea that I have here is I want to explore this Confluence space and actually go ahead and get some meaningful data out of it. So this is not a very large Confluence space per se, but I would do the same thing even in a large Confluence space. In this case, I'm just wanting to explore and chat with the Confluence space without me having to query it manually and figure out the query and learn the query language and so on and so forth. So I don't want to do all of that stuff. I just want to use LLMs. I want to use LLMs to hammer away at the problem and get me the answer I want. So the idea here, and let me explain what's happening. It's going to be finally delivered and rendered as a web application. So that's what I'm showing you here. So when I connect it to Confluence, it's going to pull the content from that space and store that in a database. So you will see that that's what's happening here. But really, the most important thing that you really need to be worried about is this one, which is the agent.py or agent.py. Here, we are using DSPy. Now, DSPy is really cool because you can extract data, you can do your LLM inference and data extraction in a structured format by default. So I've created something called a QA signature, which is basically a DSPy way of saying that this is the logic it would use to extract it. So it has input fields and output fields. So I'm just saying, I'm going to give you some context, which is Confluence pages with all titles and URLs. I'm going to ask a question, the user's question. I want you to give me these three things, which is reasoning, cited pages, and answer. I want you to come up with an answer first. Then I want you to tell me why you came up with that answer, as to what was the reason behind why you picked that answer. And then tell me which of the pages you found the answer in, so that I know you've not just hallucinated this stuff, right? So it pulls all the Confluence pages and writes it into a large string. This is what this is doing here. So all the Confluence pages written into a string, and then it's actually super simple. What it really does is that, of course, all this is logging code. I've just done this because I wanted to show logging on the chat. In fact, most of this code, if you remove it, it's not really going to affect the application in any way. So really the functional piece here is it's going to take the context, which is going to generate this huge string, and then I'm going to run it with the context. I'm going to say that based on the context and the user's question, give me an answer, and that answer is going to show up on screen on an application. And I've also, like I said, indexed some data in the database, which is basically pulling all that Confluence data, storing it in an SQLite database, and that's what is going to be used. So you will see that there is like an SQLite database which has the page titles, it has the page contents, body text, etc., which is what we are going to be using in our analysis today, right? So this is what I have. It's a pretty simple setup, and of course, I'll be sharing the code in the show notes as well. So let's run this. I've already set this up. I'm using GPT 5.4 as my model of choice today. I can use anything else. I can use different models, but I'm just choosing to use GPT 5.4. All right. So here I have this. Now let's actually go to switch space. Let's actually go ahead. And I'm going to switch space to this because this has a little bit more data than the other. So it first renders all the different Confluence spaces that I have synced. So I need to give it my API token. It connects and gets me the Confluence spaces that I have. Now I'm going to clear history and I'm going to ask a question. Now remember this space, I am asking a question to a space. Now the space has several pages, nested pages, embedded pages, what have you, right? This is what it's doing. So I'm going to ask it. So this is an app that has PRDs for an expense management system. That's what the space is actually doing and the pages are actually having, right? So I'm going to say, explain the expense approval process in detail. Okay, I'm just going to say that, just explain this. So what it's going to do, it's going to load that entire string with 718,713 characters, which is obviously a lot of characters, as you can see. So it starts reasoning, and this is what it does, and this is what I'm telling you. It starts looking for, so it says, okay, I'm going to look for pages with the term expense approval. It looks for these, it writes Python code to explore. Then it says, I found a highly relevant page saying PRD2 expense approval and workflow engine, where it explains the expense approval thing. Then it reads that page. So it uses a regular expression in Python, reads that page. And then it does another thing, which is like another approval for another type of page, which is this. And again, it writes code every single time it's trying to reason through a solution until it finally comes up with a final solution. And all of this is captured here. So I've given it a 10 iteration limit. This is more than enough. And you can see that it's done a pretty darn good job. So it says expense approval works like this. It says cannot exceed $5,000, so on and so forth. What approvers can do, they can do this. It gives you ERP rejects the record. So there are two types of acceptances in this system, both from a administration perspective and the ERP perspective. So both are correct, which is very good. So yeah, this is pretty accurate. It's something that is actually pretty accurate. Now you'll see there are sources here. I've already asked it to cite sources so that it doesn't just give me some random sources. I have also asked it to give me the reasoning as to what it found, how it found it, and why it's using this as the answer. I like doing this simply because I know that I can trust the LLM a lot more if I have citations, which is why I have citations in there. So this was pretty quick because I didn't need to use RAG. I didn't need to use any other technique. In fact, I don't have exact data for you, but I probably expended very few tokens in this process because the LLM was just writing small bits of code and then exploring the responses and then writing recursively more code, exploring the responses against a single large string variable. So that's really the benefit of using RLMs. And I found this to be an invaluable approach as an alternative to RAG, especially when you're dealing with long context problems, like in this case, dealing with a large Confluence space. So that is something that I wanted to showcase. I hope you found value watching this video, and please do like this video and subscribe to my channel if you like this sort of content. I keep coming up with these kind of practical projects. I'll also be sharing the code and the slide deck. Thank you so much.